So before I get started, who am I? Just a brief introduction of myself. I'm Niels Ben-Thielen. I'm the Chief ML Engineer at Union AI. Union AI is a ML data infrastructure company that is commercializing Flyte, which is an open source orchestration engine, orchestration platform. And my role there is to strategize, code, give talks, about the machine learning capabilities that Flyte gives you and Union AI gives you. But today I'll be wearing my Flyte hat, so I'll be wearing my open source hat today. I'll be sharing a lot of code in today's presentation. And actually, my background is in biology and public health. I kind of got into data science and machine learning while I was in public health grad school. Started taking stats classes and programming, and I sort of never looked back. I'm the creator of Pandera and Union ML and one of the core maintainers of Flyte. And these days, I like to say that I like to build open source tools for data science and machine learning practitioners. So just to give you a flavor, a sense of my particular ML journey, I started roughly in 2012. Mainly programming in Python and R, and I got my feet wet sort of training models, processing data, doing visualization. Wasn't sure exactly where I was headed, but as time went on, I got deeper and deeper into data science and machine learning. Around 2019, I wrote Pandera as a data validation tool, and last year I wrote Union ML, which is not the topic of today, but something that I've been actively developing. It's basically a thin layer on top of Flyte, which you'll learn about today, but geared even more towards machine learning use cases. Okay, so I'm going to break this talk up into 4 sections, and it's going to give kind of a high-level overview of things and kind of go deeper and deeper into various fine-tuning techniques. We'll look at some notebooks, we'll look at some code. We'll try to understand 3 specific techniques that I'll be talking about today, but they are no means all of them. And there are a ton of them these days. So that's the second part of the talk. The third part will be about kind of switching gears into declarative ML orchestration. So there's this abstraction layer that you may have heard about or may not have heard about, but it's this orchestration layer. So you know Airflow or Prefect, Dagster, Flyte. These are all orchestrators that help you reason about the flow of data and how you stitch together computations to get data from raw to desired states. So that's the third part. The last part, we'll kind of put these 2 worlds together. We'll talk about fine-tuning LLMs using various high-level frameworks and tools that make it very convenient to code up what we'll be talking about today in terms of specific methods. So it kind of abstracts that away from you. But then there are still challenges of infrastructure and package dependencies and reproducibility. And so we'll look into how Flyte as an orchestrator can be used to train these kinds of workloads. So today's learning objectives broken down into learning about what fine-tuning is, maybe as an app builder. So maybe if you're more in the software development area, kind of trying to build apps with LLMs, contrasting that with what a researcher might be thinking about. We'll also learn about how Flyte orchestration helps you, reason about computation graphs, provision resources declaratively, think about data flow, or not think about it, actually, in the case of Flyte. And then finally, we'll, in this second section and beyond, we'll dig into 3 specific fine-tuning methods. Not exactly fine-tuning. These could also potentially be applied in just general optimization of deep learning models. but we'll dive into zero redundancy optimization, low rank adaptation, and 8-bit optimization. I guess the main caveat here, my background is not in computer science, so I have about a decade worth of experience in this area, but a lot of learning, as you may know, is happens at the edges of knowledge. So we might be using tools a lot and abstracting away of all those things, and as new papers come out, you kind of have to find the papers, roll your sleeves up, learn a little bit about things, try to dig in, and maybe implement toy examples for yourself to understand things. And then obviously, a lot of good people, smart people are building packages to make these super easy to use. So that's what we'll kind of take this journey of understanding things understanding things conceptually, breaking things down, implementing toy examples, toy implementations when possible, and then going up a level in abstraction and not worrying about how to exactly do 8-bit optimization, but like using the tools, but then using orchestrators to sort of stitch everything together in a nice way. Okay, so hopefully that's clear. The first part of this talk is a motivation, like why do we want to fine tune at all? So here is a large language model. You give it an input and prompt. It spits out an output or response. You can swap this LLM out for any machine learning model, and terminology will change, right? But prompt engineering is something that I believe came out of the LLM kind of recent progress in it. So this is the ability to, since you're playing around with your input space, which is massive, unlike a traditional ML model of like fixed number of features, you can manipulate the space in many, many different ways. And depending on how the model was pre-trained or fine-tuned or RLHF'd, which we'll cover a little bit just lightly, you can manipulate this input prompt to achieve the task that you want. So for example, sentiment analysis. Before you would have to train a special sentiment classifier, but now typically these days you can just use a like off-the-shelf LLM, zero shot or few shot, learn it on the input. So give it a few examples of like text and their classes, and then more often than not, in many examples that you can see today, the LLM will be able to handle this and do pretty well. So prompt tuning is something that's kind of edging towards doing model updates. So there's a very wide number of application or specific techniques here, but prompt tuning is essentially you have some K tasks, you fix the exact tokens of those tasks, but then you update the input embedding layer, and so now you're tuning one layer in this like potentially massive model, updating it via backprop, but having the rest of these weights in the gray frozen so that you don't have to maintain the gradients and update those. Use my laser pointer actually. And then finally, fine tuning is on the other end of the spectrum where you may still prompt engineer in the end, but what you're doing here and what's not pictured is like you have some other data set that is of the data distribution that you want to capture in your task, and you update the model directly. And so this is the general class of fine-tuning methods. Will update all or some part of the model, and as we'll see, there are like many ways to think about this. So pros and cons, just real quick. Prompt engineering, a lot of these will kind of just be the inverses of each other. So prompt engineering, you have access to powerful proprietary models, basically access via API. It's It's adaptable to many, many tasks. You don't need like lower level data ML engineering infrastructure expertise. It is helpful to know like how these things work, but I think it is sort of an orthogonal skill set. You can't. I am not a very good prompt engineer, admittedly. So you could get very good at doing it. And I guess one other benefit is that the costs can be easily controlled. I mean, it can get expensive if you have an automated process, like run a bunch of prompts on your data. But generally speaking, if you're doing this interactively, you can like sort of build an intuition on how to get your task done with prompt engineering. On the downsides, the weights are not accessible. So if you care about that and you care about customizing the weights, that's not, possible. Does have limited fine-tuning capabilities in the sense that like you can few shot learn like your task. But again, that is limited. If you care about data privacy, you're yielding data to walled gardens, which, I mean, in this day and age, it's like we're giving up a lot of data anyway. But if you do care about this is a limitation of prompt engineering, assuming that you're using like an API, like OpenAI, Anthropic, etc. And you're subject to knowledge cutoffs. And you can get around this by using the LLM as essentially a token processor that hooks into other things like databases, knowledge bases, things like that. So essentially, it now becomes a function of whatever static or dynamic knowledge base you're using to like look up most recent information on the web, for example. For fine-tuning, you have full access to model weights. That goes without saying. These can be specialized to specific tasks. So if you care about just getting really, really good performance on a small suite of tasks, this could be a good way to go. You have control over training and inference data. So this ties in with the yielding data to a walled garden. Assuming you have a setup on a cloud somewhere and you trust that cloud with your data and compute, then you have full control over what goes into those models and the model artifacts themselves, and then how you do inference on them. It's better than pre-training from scratch. Pre-training from scratch is really expensive. It can be really expensive. Something like a GPT 3.5, runs a very, very high bill. On the downside, if this is an issue, it does require data ML engineering expertise. GPUs are costly. This ties into a lot of the methods that we'll be talking about today, which is directly incentivized by this. Is typically not as performant as proprietary models if we follow this narrative of the scaling laws of LLMs. And you could, at the end of the day, pour a bunch of investment, money, time into fine-tuning a model, and I guess there may be other workshops and talks addressing some of these issues, but in this conference, but you can, invest a bunch of time in it and actually not achieve your task. So that is contingent on like creating a high quality enough data set that captures the task you want, and you're testing and validating your model as you're training it. So all the kind of best practices around ML applied in this domain are relevant. Okay. So here's a little, this kind of tongue-in-cheek. It's not meant to be like super serious, but this is the kind of decision tree kind of flow chart flowchart for from maybe more of an app builder's perspective. Maybe, I mean, if you're a researcher wanting to research fine-tuning methods, this won't really apply. But if you're trying to, say, create an application in healthcare or some specific domain that is not addressable with open public, like a ChatGPT, for example, then I start at data privacy here at the top left. If you care about it, if it's a lower stakes kind of application, maybe PII is not as important to you, then highly encouraged to go into prompt engineering, because fine tuning is a whole set of investments that may not get to the ROI you expect. So you iterate a bunch of times. If you get the desired output, have you tried really hard? If not, try some more. But if you've tried really hard and still, you're not getting the performance you want out of the model for your specific task, then it might be time for fine tuning. The first fork in the road here is if you have ML skills. If not, then obviously you can build a team up with those skills. If you're doing this yourself, there are some low-code fine-tuning platforms out there. I'm not sure. I've never tried them, so can't really speak to those or recommend any as of now. But if you do have the expertise, then quote-unquote high-code fine-tuning would be the process here. So this is basically what we are going to talk about today for the rest of the talk. If you get the desired output, yes, you ship it, and then you go about developing your downstream application. If not, you can always go back to the drawing board, or you can wait for R&D to sort of catch up and overcome the limitations and problems you were seeing when you were doing things. This is not a prompt engineering talk, so here are just some links. Again, these slides will be available. So I've peppered the slides here with all sorts of links that you can go click into as basically the list of references. A bunch of companies have created courses or guides to how to do prompt engineering effectively. A lot of it, quote unquote, just boils down to writing clear instructions, but there's a lot of more nuance there. So probably worth looking into those resources. Okay. I need to increase my pace here. So moving on to the second part of the talk, how to fine-tune LLMs. I'll cover 3 types of fine-tuning in this slide. Continued pre-training, an obvious just continuation of pre-training, right? Supervised fine-tuning, and RL from human feedback. RL being reinforcement learning. So with CPT, it's not talked about a lot just because it's pretty much just the same as pre-training, but the data distribution is what's different. So instead of like the internet and all of GitHub and all of whatever public sources, you might have a proprietary data source somewhere. So you do SQL query on your company's data set, your text data. And you end up with a pile of tokens, which, high quality is always better, but the minimum bar here is it can be low quality. You pick a optimization method, and at the end, you get a text completer. So you're basically just biasing the model just more towards the data distribution, and it's just spitting out probability of next token. For supervised fine-tuning, as far as I understand, this is like specifically for, again, this all just boils down to token completion, right? But the structure of the data set kind of shapes what kinds of capabilities the model learns. So in this case, choose a pre-trained model, you create a prompt response. Sorry, I will pop into the questions in just a second to just see what's in there and maybe address some things. So yeah, you create a prompt response data set. So prompt This is a statement made by someone. Response would be sentiment, for example. Or this could be more complex things like write a poem and then the response would be a poem. Here with supervised fine-tuning, there's a few other optimization methods that sort of open up that you could apply for pre-training, like parameter efficient fine-tuning. But as we'll see, there's some important things to know about that. And in the end, you have a prompt responder, which is a special case of a text completer. It's just able to better respond to things if you have a clearly enough stated prompt that it should respond appropriately. And finally, with RLHF, many of you may be familiar, but you essentially create a prompt multi-response dataset with human preference metadata attached to the responses. Sorry, just to pop back, minimum quality of this would be high, similar to the RLHF dataset. This is very complex, and I'm waiting for the open source sort of like implementations of this. I think there are a few out there these days, but I still need to dig into that. But essentially, you build a reward model. You initialize the reward model from your supervised fine-tuning model. And this reward model can be formulated in various ways, but it essentially learns, it essentially takes a prompt, a response, and it can score what that response is. So it can do this by various ways. A simple way would be your training data has winning response, losing response, and you basically train a classifier to say which one is which. Once you have the reward model, the reason we do this is to essentially capture what human preferences are so that you can then train a policy that doesn't rely on like some finite set of annotated data, and now can use a reward model to fine-tune a policy on top of your SFT model. And in the end, you get a more aligned prompt response responder. So it will do the same things, but it will know about what people tend to like as responses and give those responses. This workshop will focus just on these first two, CPT, SFT. Okay, so let me just hop into the questions real quick. Okay, so a question here. When you say data privacy with prompt engineering, are you referring to proprietary models like OpenAI? Yes, so that is like the big assumption is if you are prompt, that is my big assumption here, is that if you're prompt engineering, you are likely using a very powerful proprietary model. Those are also separate, right? So you can have a very powerful model that's open source, right? But today, these tend to be proprietary. And especially when if you're an app builder, you're trying to do something fairly novel and you're not sure if it works, you generally want to try the best of the best model to see if like the current state of the art can actually achieve your task. If yes, then you kind of like go down and scale back, and maybe you'll go to an open source model. You'll see if the same prompts work with those. So a lot of assumptions here. Great questions. So thank you. Keep these coming. Okay, so the next part of this section of fine-tuning methods, kind of like tutorial style, I'll hop from this to a notebook. So the first topic we'll cover is just transformers redux. I'm sure many of you, maybe all of you know about this, but I think it's worth kind of motivating the reason why fine-tuning is important today. This directly leads to, thinking about memory and thinking about compute, mostly memory, like how much memory do I need? And that directly informs purchasing decisions of GPUs or looking at various cloud infrastructure to see, what GCP or AWS instance I need to like even feasibly train this model. Then we'll get into our first specific technique, zero redundancy optimization with deep speed. So deep speed is the Microsoft implementation of this framework. I'll also give a brief intro to 8-bit quantization, and maybe not so brief. And then finally, they'll go into low rank adaptation. This is a class of parameter efficient fine-tuning, or PEFT method. So a lot of acronyms here. Hopefully by the end of this, you'll be able to use these comfortably. All right, so transformers redux. What's the problem with bag of words? So, I feel like I can say, back in my day, these days, even though I know there are people who have been in this field for much, much longer, but it feels like for me, my first NLP models would be of this flavor, right? So you have sentences, you essentially have a fixed dictionary, you lose, the problem with this is you lose all ordering. So you just have counts, and then you might have, TF-IDF, if you can recall that term, ways of normalizing this table such that, you get around various limitations like normalizing long versus short sentences, things like this. So this is like the simplest thing you can do with essentially symbols, tokens, right? So then there was word2vec, remember those? This is a set of techniques where, if you look at the left-hand side, continuous bag of words, essentially have a sentence, pineapples are spiky and yellow. And the projection here would be a set of neural net weights. And you would project some kind of token representation of these inputs and try to predict the word spiky here. So essentially the output word is based on the context surrounding that word. And so this context window of, I guess 2 or maybe 4, depending on how you think about it, that's a hyperparameter you play around with to increase the context window. For skipgrams, you kind of invert this model, but essentially the idea is very similar. It is based on some token embedding representation, or based on some token, create an embedding representation that captures something about its surroundings. So this is actually a very important idea that transformers or the attention mechanism has as well. It's just kind of, on steroids. Okay, so very brief. This is, again, a very brief history of these things in NLP, right? So the next major innovation is RNNs. I believe that there is some architecture development here recently with RKWV. I forget the exact acronym, but so essentially RNNs allow you to take in variable length inputs, produce variable length outputs, and it does this, with the hidden layer here, which can be expanded. So this is just at the highest level, but when you unfold this over time, you can feed it these inputs. It takes that feeds in, that determines its hidden state. Things like LSTM have an additional kind of memory that's passed on over time. So that was meant to overcome the vanishing gradients problem, where if you have long sequence length, by the time you get to the beginning of the sentence or paragraph, the gradients will be so small that it's not going to learn anything in terms of like long range dependencies. So LSTMs and GRUs, things like that, got around this by having a separate memory set of memory weights that allow information to pass more easily through this component. Okay. So now with attention, you have essentially, again, a sequence of tokens. And so it represents those collection of tokens as queries, keys, and values. So this is like, as a token in a sentence, the cat sat on the mat. As the word cat, like, what am I looking for? So that's what this does. A key is, of all the other words in that sentence, like what what query should align well with me, right? So that's keys. And then values is, so the first, you take KQ, you normalize it by dimensionality of the embedding, do a softmax, and essentially what you get is attention weights. And so it's the cat side on the mat, you know, you have as the word cat, like what am I paying attention to in my context window. So then you take the values for each token. The values are basically like, what information do I want to give cat, you know, or the other tokens in this context. And at a very high level, you know, we're breezing through this, right? This is what attention gives you, is the ability to sort of re-represent yourself. I'll get to this later. This is the architecture, very famous diagram right now. I feel like components have been moved around since then, since this original paper, but the main idea remains. So again, this GIF is actually quite amazing. I remember first seeing this and not really understanding, but now after many years, it makes sense. So like essentially, each token in self-attention is able to re-represent itself based on its context. So when I say the riverbank and I went to the bank for money, the word bank there by the end of like multiple layers of attention will look very different in embedding space than in those two sentences. As opposed to if you think of bag of words, it's all the same as far as the bag of words model is concerned. So what's the problem with attention? It requires a lot of memory. Each attention layer has quadratic complexity and is bound by fixed context length. And so these all are important, right? So if you want to model longer dependencies, if you want to model an entire book, right, you need the whole context. You know, that's going to blow up in complexity very quickly, and it's going to be, you know, very, very hard to train. So essentially, more powerful models are blocked by context length, potentially. And the larger your context length, the more memory you're going to require, more compute you're going to require. So if you can somehow make the memory requirements less, make the throughput of when you're doing backwards and forwards and backwards passes, you're going to be able to train models faster or train larger models on like a fixed set of fixed infrastructure. Okay, so how much memory do we need to train a model? So there are a couple of assumptions here. We're using the Atom optimizer, which is a stateful optimizer. But if you're assuming FP floating point, you know, single precision, floating point 32, you have to keep track of a bunch of things. You need, first of all, your parameters. You're going to need some kind of temporary buffer for activations. You're going to need to store your gradients, which is essentially same, takes the same amount of space as your gradient or as your parameters. And then for Atom, you're going to have to keep the momentum and variance of the gradients. So these are the two parameters that Atom keeps track of. Other optimizers will have different optimizer state requirements. But you know, back of the envelope, if you have 100 parameters, you'll need about 200 bytes of memory. Hopefully my math here is correct. If you have 1 billion parameters, you're going to need about 20 gigs of memory for assuming single precision. So one of the things you can do, right, is you can do mixed precision training. And in some cases, in some setups, the reason you'd want to do this, right, is you represent your parameters, gradients, activations as floating point 16. So this increases the throughput of your forwards and backwards passes. But to maintain the stability of the optimization step, which gets you the gradients, you're going to have to, you know, under this framework, keep single precision. So this actually, you know, depending on the setup, can save you memory, but it still has some additional overhead here. So some methods to train large models, right? Just want to give you some background and kind of give you a survey of various techniques you're probably familiar with, right? Is gradient accumulation. You can have some stated global batch size you want, but only a certain size, say 4 examples, can fit. A batch of 4 can fit on your GPU. So if you want an effective batch size of 16, you break that up into 4 different gradient computations, and then in the end you can just aggregate them here, sum them up, or average them, depending on what you want to do, and you get the batch size that you desire. For model parallelism, you actually have 4 GPUs. Your models doesn't fit on a single one of them, so you kind of partition the model across the 4 of them. This causes issues about intercommunication between nodes, but if this is the only possible way to do it, then you have to shard your model and compute activations here, pass those activations to the next machine, so on and so forth. Now, to train models faster, there are innovations in optimizers. So here, according to this chart, Atom converges very quickly. There are schedulers as well. So one cycle scheduling, cyclical scheduling of the learning rate has been shown to improve convergence. And then data parallelism, where you have 4 machines, and now you have each machine, you have a copy of the entire model in each machine, you have it process batch size of 4, you aggregate the gradients again together to get an effective batch size of 16 in this case. Okay, so hopefully that gives you a sense of the lay of the land in terms of why it's very important to think about memory, think about how to fit various models and different data type based on different data types, different distributed training setups and stuff. So the first specific technique that I want to show you is zero redundancy optimization. So zero takes ideas from data and model parallelism. So there is sharding of model weights, but as you'll see in a second, this is a data parallel technique, but it's done in such a clever manner, in my opinion, such that you can massively decrease your memory usage. So on the left-hand side here, just at a high level, right, you have n GPUs. This is full data parallel. This is a full data parallel setup. You have different n batches of data, full copies of the model. So we're all familiar with this. With zero, you shard your model into n parts, and this is just the beginning point, right? So shard it into n parts, and so you could potentially use a much smaller set of GPUs, distribute the weights across the cores, and fit a much larger model than you would have otherwise on a full traditional data parallelism. So there are 3 stages to zero parallelism. So if we take our baseline here, right, the blue is the parameters, orange is gradients, and green is optimizer states. Just doing a quick time check. The first stage is to partition the optimizer states, since, as we saw earlier, this takes up a whole bunch of memory. So if you can shard those first, you're going to be able to save a lot of memory. This is about a 4x memory reduction compared to baseline. The second stage is you shard the gradients as well. This leads to an 8x memory reduction. Then finally, the third stage is you shard everything. And you essentially get a memory reduction that's linear to your data parallelism degree, right? So yeah, if you have 32 machines, 32 cores, yeah, that's 1 over 32. So that's pretty nice. It's fairly involved, so I'm gonna actually play this for you. Oops, didn't mean to do that. I'm gonna do 2x speed, and I'll kind of do a running commentary. This is a video created by the Deep Speed team. So you have a bunch of data. You can see what each cell represents. For parameters and gradients, we're using floating point 16, again, for that throughput benefit. For optimizer states, we're using FP32, again, for stability when we're computing the gradients and the weight updates. So the first step right here is we have 4 GPUs. We're sharding the model state. So each core in this diagram owns, essentially, is the owner of a piece of the model. So you can think of these as transformer layers, right? So we initialize the first forward pass. And as you can see here, we're doing an all gather operation. We are the GPU 0, owner of the M0 here, is splitting, or it's giving its weights over to the rest of the cores. And they're processing just the activations, and they're doing the forward pass across all the 4 parts of our batch. We continue on, right? We keep doing this, and I'll skip forward a bit. Keep going, keep going, keep going. And at the end, you have the loss for each shard. So notice there's a little overhead here for temporary buffers for when we do these all gather operations for the parameters and gradients, but we get rid of those when they're not needed for a particular part of the forward pass. Same thing with the loss. Again, the parameters are distributed again for the gradient calculations. And then what was just shown is once you have the gradients across the cores, they are then an all reduced step, or reduced step is done. The gradients are accumulated on the owner of that segment of the model. So this happens layer-wise, in a layer-wise fashion, until all the gradients are obtained. And now those are cast into FP32, and now the optimizer is run independently, since that is something that you can parallelize once you have the gradients per shard. Once the weight updates are obtained, they are then cast down to FP16, and then those are applied back to the parameters. So hopefully that that was kind of quick, but again, you have access to these slides, so you can check these out on your own time. Oops, where am I? Okay. So in pseudocode, right? Oh no. So the video was not working. Okay, well, hopefully you can check that out later. It's quite informative, but okay, just moving on. This was essentially what the video was showing. Essentially, for the forward pass, you iterate through your layers. You do this all gather operation here. So you distribute the shards across all your GPUs just for that one layer. You do the forward pass, and then you discard the weights except for the owner of that particular shard. So then you have the loss, and then you do the same for the backward pass. You iterate through the layers. You do an all gather of the weights because they're needed for the gradient computation. Do the backward passes, and then you do a reduce scatter, which is just this operation where you aggregate all the gradients again. in the core that owns that part of the model. Okay, so that's a very high-level summary of the Zero framework. There are a couple of tools out there that implement this with various variations. But the idea, again, is we are going from the state where we have to copy the model weights across all the cores to just copying 1 over n, or maintaining 1 over n memory across your cores. And then there is some like a little overhead as you're distributing the weights and accumulating gradients and so on. Okay, so the next part is an intro to 8-bit quantization. So at a high level, as you can see in this diagram, we have a 32-bit floating point number. We can quantize it to an integer, 8-bit integer, and now you can fit larger models in your GPUs, but you've lost a bunch of precision here, which is actually quite important for the backprop algorithm. So to give you a sense of this, I want to take a notebook sidebar. And here's the link to it. This should all be openly accessible. Actually, let me just copy paste this into the, actually a bunch of you are in here, so that's great. So I'm just going to hop over to this notebook to give you a sense of one like 8-bit quantizer technique, right? So it's called ABS-MAX. What you do is it's an 8-bit representation of a float. You basically, it's like binning. If you know normal distribution, if you like do a histogram of the normal distribution, you come up with a bunch of bins. This is essentially what you're doing with floats. So you normalize your floats to a range of -1 to 1, and then you can bucket them into discrete buckets ranging from -127 to 127, so 256 values. And you do this by taking the absolute maximum of your data, right? So this is data dependent. You apply a scaling factor to your original vector. And that's the first operation we're going to do, right? So here's our data. We have various values. Now we apply our quantizer to it. And as you can see here, quantized is maybe like, I can copy paste this back up here just to show you just the memory used, right? So obviously, you see the code here. We started out with a float 16 half precision vector, and now the quantized vector is 8int8, which takes half the amount of space, right? So now the limitation, this is a lossy process. So reversing it is simply applying or dividing by the scaling factor and casting it back to float 16. The problem here is now if we look at original data, this first value is 1.2. It dequantized to 1.189, right? So could be a problem. And this is like error analysis of this is like one of the things when you create a new quantizer algorithm, right? So all in all, right, we have our original, we quantized it, we dequantized it back, so it takes the same amount of space, but now we have some error. So if we visualize this error, it doesn't look like a big deal, right? It, just from the scale of this plot, looks fine. However, so this is just like the errors, from the original to the dequantized. But what if I have outliers in my data? So now I have this -17 value, right? As you can see here, the errors become massive. And actually turns out during backpropagation, it's the larger gradients that matter And so this justifies the whole using single precision instead of FP16 for optimizers. So hopefully that gives you kind of an intuition of how quantizing works. Now hopping back onto my slides. One algorithm I want to highlight here is 8-bit optimizers via blockwise quantization. This is work done with Facebook AI Research and Tim Detmers. He and team have been putting out a lot of great stuff recently. And this is essentially how this particular algorithm works. So to deal with the outlier problem, they chunk the data into blocks. So think of like the gradients or any of the optimizer states. They chunk those into blocks. They apply the absmax, algorithm that I just showed you with a slight variation of using dynamic quantization, which I'll get to in the next slide. But basically, if there's a few outliers in a couple of the blocks of your data, it is the imprecision, the potential issues are isolated to those number of blocks. Dequantization is pretty much very similar. So you take your lookup indexes that are stored in int8, you reverse the process to get back your original values. So this piece right here with dynamic quantization, I don't want to get into it too much, but it essentially is a variant of dynamic tree quantization, which is just a way of representing like floating point numbers. And so there's an exponent bit, there's a sign part, there's an indicator bit that can actually slide around, and that determines how precise or imprecise your data needs to be. And this last part is the fractional part. So 1001 translates to 0.6 times the exponent. So that's what the number would be. But as you can see on this left-hand side, with linear quantization, right, it's just naive. So 0 to 100, 256, each of these will normalize back to whatever your data distribution was at quantization time. Whereas quantile or dynamic quantization, if you slide from 100 to 150, it's going to normalize to around the same value. And so this method actually is more precise for larger and smaller values of your data distribution. So this is what we care about actually in the during the backprop optimization process. So why go through all this trouble? Well, you can see here 32-bit and 8-bit classification errors by epoch, and you can see essentially no difference, at least in this case. This is an ImageNet, AlexNet training trace. So you can get huge cost savings, basically a 4x reduction in need. So you have 100 gig memory requirement for training something, then that goes down to 25 gigs of VRAM. All right. Last fine-tuning method / training method I want to highlight is low rank adaptation. And by the way, the 8-bit and 0 these are not fine-tuning specific, right? But these are these are used in the special case of fine-tuning as well. So with low rank adaptation, it's worth just kind of breaking down regular fine-tuning, right? So you have some weights W, you get the backprop results, delta W, to update the weights, W prime, you just add those two together to get your updates. So doing a forward pass on this is H equals W prime X. Just hopping back on the chat. Yes, maybe there are some great resources out there. Thanks for sharing. Okay, so Another way of formulating this is we keep the weights, the frozen weights, the pre-trained weights, and the weight update separate, which is kind of weird, right? But mathematically equivalent. Why would we want to do this? We are keeping 2 copies of our weights. So this does not make sense in that naive case. But with LoRA, the formulation is this. So suppose your weights are A by B matrix. You can actually decompose this into 2 smaller matrices, right? So WA and WB. And as long as when you do the matrix multiply, they are of the same dimensionality as your original weights, you should be fine, right? So if A is in the space A times R being something I'll describe later, and B being R times B, when you multiply these together, you get A times B. And you can essentially, if you initialize things correctly, so if you initialize A by this normal initialization, and you initialize all weights of B to 0, meaning at the beginning of training, it's going to be all the pre-trained weights. And then as you do backprop, the A and B matrices should change. So this being normally initialized will break the whole symmetry breaking problem of initializing all your weights to 0. So this should be fine. So if you buy into this, you can actually get the same thing as W prime X if you do WX plus the stand-in for delta W, WA, WB. And so R in this setup stands for rank, and it places an upper bound on the rank of your adaptation matrices, where rank is the number of linearly independent columns and rows of a matrix. So I'll show you an example, extreme examples later of this, but you can think of this as essentially mapping onto model capacity. Is the hypothesis being that during pre-training, delta W has a high intrinsic rank. So when you're training on the web, you're going to want a high capacity model. Just a pictorial representation of a full rank model. It's just the identity matrix. Like there's nothing in here that's linear. There are no linear combinations of certain columns to give you other columns. Whereas this one, right? This third column is column 1 minus column 2. So this is a rank 2. So it is not full rank. So you can imagine such a weight matrix with a lot of linearly dependent columns. So the hypothesis is that when fine-tuning on a specific task, you have a giant pre-trained model, but the actual rank of the weight updates, delta W, is not as high as whatever the full weights are. So it justifies doing this transformation here with the lower R. So imagine if A and B are equal and R is equal to A and B, you basically recover, the full delta W weight update. That's what I just said. So it does well in practice. So according to this fine-tuning set of experiments done in this paper of GPT-3, this 175 billion parameters, get orders of magnitude reduction in trainable parameters with what it seems like better, if not equivalent, at least performance on certain tasks. Okay, next notebook sidebar. So this is the last notebook sidebar. Oops. Need to reconnect. Hopefully this all, oh no, okay. Well, I'm not gonna run the code actually, but here's a very basic LoRA implementation. So and skip all this training boilerplate. This essentially is a training code for MNIST. But here's our model, very simple model with 3 fully connected layers. We flatten the image data. We pass it through some ReLUs, do a log softmax, and yeah, that's pretty much it. So that's the model. So if we run this, just a sanity check, loss decreases. We get a 98% accuracy on the test set with 128 hidden dimensions. So let's create a LoRA layer. So what's going to happen is this LoRA layer takes in a linear layer, and it freezes that layer when it requires grad equals false. And it creates these 2 parameters, these 2 weight matrices of dimensionality, input dim of the original weights, and rank, then rank to output dim. We initialize them here. And for the forward passes, self.w is not going to maintain any of the gradients, but WA and WB will. And this is essentially, in code, what I showed you earlier in the slides. Here's some just extra nice things for printing. And I have this function that does a bunch of hacking of a particular model. So prepare LoRA model will just swap out things that you want to swap out under this layers string list. And you're basically replacing the linear layers with the LoRA linear. So if we run this, we see the loss is still decreasing, right? And we're using a rank 16. So sorry, I'm really bad with arithmetic. Yeah, 8x reduction in number of trainable parameters. Keep in mind that you will still need to keep the original model weights, but it will just be the parameters itself. You won't have to track anything about it. So it's a difference. These are some differences. So basically a 5x reduction in the trainable parameters. However, when you plot the losses, right, it makes sense here that this model is much lower capacity, right? So it takes longer to train and converge to the same loss. So hopefully you can take this notebook, play around with it, get some intuition on how to implement, your own LoRA layers. All right. So with LoRA, the last thing I'll say is, you can keep the weights separate. This does incur additional inference time depending on how big these matrices are. Or if you have like a single application and you don't want to incur that inference penalty, then you can just merge these back, into the original weights. Or you can embrace the additional inference time. And if you have, K use cases that you're fine tuning, you can maintain K models. And then in your application, you can imagine like I'm using, the 10th set of weights. And so you can pull the pre-trained weights and then that together. Then obviously you could keep memory, or if storage isn't an issue, you can just keep a bunch of these, for each of your K applications. All right, so last part of the talk, I'm gonna have to go real fast here. But we've learned a bunch of specific techniques, but now, how do we orchestrate all these things? How do we do it in a production setting or in a way that's reliable? So orchestrators are a class of tool that can help us do this. And these are tools that coordinate the logical flow of computations that are needed to get data from a raw data set, process it, split it, train a model on it, and then deploy that model, right? So it helps us reason about the flow of data, what the inputs and outputs are, what kinds of resources you'll need for each of these nodes. Maybe you need just GPUs for this, but not for the get data step. So it helps you, reason about the computations you need, data flows between those units of computation, what types, data types you're using, and what's the state of your data, what dependencies each unit relies on for it to do its computation, and what resources each unit has available to it. So Flyte is a production-grade orchestrator that unifies these three different kind of areas, but different but related areas, right? But it does have specific abstractions for machine learning, has just specific abstractions for data, and also for analytics. And you can kind of like see all of these things happen on a single platform. So high-level overview of Flyte is you write some Flyte code, which I'll show you a little later. This essentially compiles to a execution graph. You can think of this as a directed acyclic graph, even though Flyte does support recursion, but I do not recommend. You then package and register this into a Flyte cluster. We're not going to talk about the infrastructure piece of what goes into, a Flyte cluster, but this is essentially software stack built on top of Kubernetes that allows you to take your compiled workflows, container specifications for what each of these nodes are dependent on, some configuration, and Flyte takes care of scheduling and figuring out how to execute your particular workload on K8's infrastructure. K8 being the shortening of Kubernetes. So the smallest unit of compute in Flyte is known as a task. And these are containerized and fully versioned and strongly typed. I'll show you what the code looks like a little later. The way you string together different tasks is in this workflow abstraction, where data flow is a first-class citizen. Because you have a type system, it allows Flyte to take care of serializing and deserializing data to and from the different tasks in your workflow. Workflows are also versioned and strongly typed, so you can have workflows within workflow. A launch plan is essentially an abstraction on top of workflows that allow you to add additional specifications of how, if you want to run it on a schedule, you want to, load it up with some default arguments. And dynamic workflows are supported in Flyte, where if you have an input that affects the actual shape of the execution graph, you can do that. You can give it some hyperparameters you want to tune over, and the shape of the graph will dynamically handle that. Flyte allows you also to partition your space, so isolate resources, isolate permissions, things like this across projects and domains. Projects being semantic categories of things you want to group together, and domains are sort of like the production pipeline, the production assembly line of going from development to production. Flyte also has very strong opinions on how to do orchestration. So for example, type safety is a very important aspect, where because Flyte requires you to use Python's type annotations, Flyte also has SDKs in other languages that have types. But in Python land, when it respects those type annotations such that if I try to compose this workflow together, the Flyte compiler will say, hey, these types don't match. Flyte, even though the SDK, the workflow composition and syntax can be written in the language in Python, Java, or Scala, you can actually build containers containing code in any language, like in this example, R, and you can then thread those together into your Python workflows. Flyte also takes care of declaratively, you say what the resources you want. I want GPUs of this number, etc. And Flyte will handle finding those resources as long as they're configured in your Flyte cluster, tearing and setting up and tearing down, ephemeral Spark clusters, Ray clusters, DAS clusters for various, ML or data processing workloads. You can also, I won't show this today, later in the demo, but you can also specify your dependencies declaratively. So this is a fairly new feature that allows you to say what your image spec is. You can have different image specs at the node level. So each task can have a different set of dependencies. Just have to be careful about writing your code a little bit, but this gives you the flexibility of, say, using a PyTorch container, but in this case, it's sklearn, and like another task that uses pandas and NumPy. Data persistence is abstracted such that, if you have certain things like ints and strings and lists are stored as literals in the Flyte metadata store, so they're actual, in this case, protobuf values. But if you're storing anything like data frames or anything, files, directories, those are actually outside of the Flyte cluster, and you can configure that separately. So the metadata here is passed from one task to the next, and it's only these, tasks at runtime that have access to your raw data. So that adds a little bit more control over who has access to what data, even in a single workflow. So that's a very quick introduction to Flyte. I only have 13 minutes left, so I do want to get to this final section of the talk, and I'll just show you what a Flyte workflow looks like for these two use cases. Where for continued pre-training workflow, I'm gonna grab some subset of Wikipedia. I'm gonna fine-tune the Red Pajama 3 billion parameter model on a T4 8-core GPU. And for that, I'll need the 0 optimization with deep speed. We'll publish this to Hugging Face Hub, so we'll take a look at it. We'll also quantize it in 8-bit so that people can play around. You can play around with this on Hugging Face as well, and it'll be faster to download, and so on. And then we'll hop into some notebooks to look at what how you would evaluate and interact with these models. For the supervised fine-tuning workflow, we'll simplify the task. We'll combine the getting data and fine-tuning the model into the same task. Alpaca is a chat GPT, or I forget which one, GPT 3.5 or 4. I need to look at that, but it's a synthetic data set with prompts and responses and instructions. And we're going to fine-tune the Red Pajama 7 billion parameter model with 8-bit optimizers and the LoRA adapters. We'll publish this also to Hugging Face. By the way, all of this code will be open source. It is open source. I'll provide some links, and you still need to do a bunch of code cleanup, but they work on Flyte infrastructure. So without further ado, in 10 minutes, I'll give you a very quick tour of Flyte. Let's see what's going on here. Okay, excellent. So maybe I can increase the font size here a little bit. So here's my CPT fine-tuning example. It's just Python code, as you can see. I'll focus on just the tasks, right? So as you can see here, I'm using a pre-built container. I'm using a custom pod template, actually. So Flyte allows you to use Kubernetes abstractions, even though we try to hide it from you. We're gonna get the data. So we're gonna get Wikipedia data from our config file, which is here. So it's just a config file. We're gonna ask for, this is just a CPU workload. So 8 CPUs, 8 gigs of memory, 8 gigs of thermal storage. We're gonna use the datasets, Hugging Face datasets library to grab the data. We're gonna actually use Pandera, which is the data validation library, to try to check, I mean, I know that Hugging Face probably has some good data checks as well, but it's always, worth it to do validation. So we've defined a very simple Pandera data frame model. So if you're not familiar with Pandera, it's essentially, this syntax is essentially like Pydantic style or data classes style way of defining what column is in your data frame, what type is of each column, and then some additional just like basic checks, just to make sure like titles aren't super long, text isn't super long, and the URLs are actual URLs. We're gonna, just run this get data task, and I'll run the workflow actually in a second, but just to move on to the next task, you can see here that the task configuration is different here for the training function. As you can see here, we're actually using GPUs here, so 8, with different various memory requirements. And we're using this elastic config, which is actually a plugin that Flyte provides that gives you access to PyTorch distributed, PyTorch run for distributed training. So I could specify more nodes here, so that'll up my number of instances I'm using, but for now I'll just use one T4 node. I'm actually, true of the get data step, we're actually caching each of these steps. So, and saying, if there is some kind of network error perhaps, then I want to do at least 3 retries. This really works well with interruptible equals true, which allows you to use spot instances. So that those will be interrupted at a high probability, and Flyte allows you to checkpoint your progress. So even if you're interrupted, you won't lose all the time you spent. You can kind of embed some environment variables here for things that are not sensitive. For things that are sensitive, you can provide secret requests. So this gives you the wand, my weights and biases, I call it WAND-B. Weights and biases API secret key, so that we can track our training progress. And here's the body of the task. I'm not going to go through it, but essentially, in too much detail, but essentially, you get some training arguments, you load the pre-trained models from the base model, in this case, we're using the Red Pajama 3 billion base. Load up the tokenizers, and then enter the training loop, after which we save the model. So as you can see here, we're saving the model to a Flyte directory. So a Flyte directory will automatically save the local directory of wherever this task is running, and it will dump it into S3, as we'll see later. So actually, let me come out here and run this. So Flyte has a PyFlyte run CLI command that allows you to target specific workflows. So it's targeting the fine-tuning workflow we have here in the bottom, which is essentially getting data, training the model, quantizing it into 8-bit, and then saving it to Hugging Face. Oh, wait. Okay, yeah, I totally forgot to share my entire screen, so let me do this. Oops. Apologies for that. So I'll do a very, very quick rundown then in this case. It's going to be very hard for me. Okay, great. I'm going to keep this actually down here so that I can kind of pop it back up. So let me actually go to a successful execution in Flyte, and I'll work backwards. So this is a Union AI hosted Flyte cluster. So this is Union Cloud. It essentially gives you all of Flyte's functionality with a few more bells and whistles. But what I'll showcase today is available on Flyte as well. So here's our workflow. We are getting data, we're training the model, we're quantizing it, and then we're saving the models to Hugging Face Hub. So just so I can prove to you that this all worked, this is the 3 billion fine-tuned model and the subset of Wikipedia. I have it preloaded, although now I need to reconnect. But this is a notebook I'll also make available that allows you to do inference on this. Unfortunately, Hugging Face, the free tier, doesn't allow you to generate on floating point 16 configuration. So this one is floating point 16. It'll just time out. So there's this notebook here that I'll share that I'll add to the slides if it's not there already. So you can load this, and I ran Alan Turing was, and since I know this was an entry and it's probably already been pre-trained on this, it was able to give me a pretty decent response here. So to hop back onto the code, I'll rerun this again. Just run through this again, where this is what Flyte code looks like. It's essentially just functions, right? So we really did embrace sort of like a functional programming paradigm that allows you to reason about these things without holding too much state in your head. So for the get data step, we're just one second. Let me minimize this. We have 2 minutes, so hopefully you can get a sense of the power of writing things in code, orchestrating things in code. There are orchestrators that work with YAML, but and they're like purely declarative, but this actually gives you best of both worlds, where you have some declarative syntax, and then you still are able to drop down to like an imperative style program in Python, where you can implement the steps of your computation. So for the get data step, we're just using CPUs and this pre-built container image. We're loading the data, validating it with Pandera. So just to show you what a Pandera model looks like, this will validate the columns, their types, and the various other constraints that you might specify. And with 1 minute left, I'll show you. So this is essentially the declarative syntax for provisioning various resources. So we're saying we want to cache this execution or this task when we execute it. So if we give the exact same inputs, it won't rerun the computation, it'll hit the cache. You can increment the cache version. You can use any string that you want to invalidate your cache. We're using the PyTorch run elastic plugin here, so that allows you to tap into distributed training, the PyTorch run, the Torch run distributed training framework. We're using 8 GPUs here, so Flyte via Kubernetes will find the appropriate infrastructure for you. And in this training step, we're outputting a Flyte directory which maps onto this output, which, as you can see, is just a S3 path. So this actually will contain, if we go to the Hugging Face Hub output, all these files, right? And as you can see here, this is the main PyTorch model. It's about 5.6, 5.7 gigabytes. Compare that with the quantized model, and I see I'm at time, and that is about half the size. So I don't have time to go into the LoRA fine-tuning script as well, but it's essentially the same thing, but it uses the PEFT package, PEFT package to implement LoRA and bits and bytes for the 8-bit optimization. And yeah, I'm at time, so I'll add the links to all the notebooks so you can check them all out. The last thing I'll end with is basically, if you care about applications, then prompt engineering is probably the way to go. But fine-tuning is a good option if you've kind of exhausted all your options. There's a huge space of architectures, optimizers, and fine-tuning techniques. We've only covered 3 of them today. Flyte allows you to orchestrate these various pieces in a reliable and reproducible way, allowing you to specify resource requirements and data flow. And it also integrates with the machine learning and data stack. So thank you for sticking around past time. You can talk to me. Actually, I'll stick around here, but you can also talk to me in person tomorrow and the day after at our booth. I tried to upsample this very low-res image, but we are in right by Skyroom here. So if you want to learn more about Flyte, Union AI, if you want to chat about any of the things I've talked about today, yeah, I'm happy to talk at the booth. Okay, yeah, I'll stick around. If anyone has any questions, I can answer them here. Yes, Parth, the code is available to experiment with. Let's see, if you join the Flyte community, that's probably the best, because setting up a Flyte cluster admittedly is not the easiest thing. So especially with all the requirements that we have here, we do have a sandbox deployment that allows you to quickly spin one up. But let me actually share the code. So all the fine-tuning code that I showcased is here. Inference notebook is here. I'll add all of these to the slides, by the way, so you'll have access to them. Yeah, Wilhelm, the main thing that, so if you have a very fairly like, shall I say, if you have a setup that is already optimized to AWS step functions, it is a AWS product, which tend to be very stable and have all the benefits there. But Flyte, as you saw very briefly in my screen share, it allows you to write orchestration code in Python, and it has strongly typed syntax and enforcement and customizability such that you can write like anything that you have access to in Python, you can write it there, and like that it's just, I would say that's like the biggest difference point. There's a lot more to say about Flyte in terms of how scalable it is. So it does scale to tens of thousands, if not, in some cases hundreds of thousands of nodes. So that tells you like where it started in terms of use cases. It started in a production use case at Lyft. So that's from the spectrum of like, if you prefer writing your orchestration code in Python, there are other tools, right? But Flyte is one of those that allows you to do that, all the way to the declarative piece using Kubernetes. It allows you to, provision a flexible set of infrastructure across the tasks in your workflow. But that said, I haven't actually personally used AWS step functions, so it's hard for me to like make a direct comparison. All right. Thanks everyone for sticking around.